So, hey guys, welcome back to my channel. My name is Ash, and today, I've brought you a very interesting, video. This is the first time, I'm actually doing a video where my actual face is recorded. Not a video; it's a kind of a lesson, anything you can call it. So I'm not that experienced in um, the topic recursion, which is today's topic, and in anything like RM, IOQM, anything. So, so if you want to watch more videos like this, and if you want to actually watch, if you want more lectures on certain topics, just comment it down in the comment section, and I'll surely try to make a video. So today's topic is actually recursion or recurrence, and this is just a question from IOQM 2023. And if you're able to do this, you don't actually need to watch this lecture. It's not going to be super advanced. But if you actually aren't able to do this, you might want to consider watching this video. This is a good question. So yeah, I'll teach it from the basics. So let's start. What's recursion or what's recurrence? I'll call it recurrence. Some I don't know the spelling correctly, but yeah. So what's recurrence? I'll teach it to you with a quite good example. Um, it's like um, you know, recurrence is very complicated. There are two cases of recurrence, like being in maths. One is for combinatorics, which is the main thing that we are going to do today, and one is for other things like Fibonacci, Fibonacci, etc. So my handwriting is pretty bad. So yeah, like sequence and series. We'll learn this in JA, etc., which I have not, but yeah, you just need the combinatorics one for now, for IOQM especially. So I'm just going to teach the basics that you need to know. The most famous kind of recurrence is Fibonacci sequence. Sequence. Now, what is this? I'll explain this to you with an example, with the game. Let's suggest. When I was 2 to 3 years back, I used to think that I found it something quite new, which is one of the most famous recurrences. And you guessed it right, it's the Fibonacci recurrence. What did I do? I had actually not done anything like huge. The only thing that I had done was to take a grid like this, okay, stand it here. I took a grid, I wrote numbers 1, 1, and I proceeded to add 2. I would take 2 this side, 2, and I would take 1 this side. So basically a diagram, a crisscross method. 3, 3, and 2. 5. I take it this side. 5, 3, 8, 8, 5, 13, and this goes on. One interesting thing that I had noticed is, let's call this block Tn, T1, T2, T3, so on up to Tn. I noticed this Ti by Ti plus 1 is actually equal to a certain constant. I don't remember the constant, but it's the golden ratio. 5 by 8, 5, 8, 0 0.6, 8, 2, 0, 2, 4, 8 something like 0.662 8, something like that. So it's 0.6 to 0.7, and it always summed up to a constant, which we know as a golden ratio. That was quite interesting for me. Another interesting thing that I noticed is, which is quite obvious now, like when you've developed logical thinking, this showed an amazing sequence. Just like this. 1, 2, 3, 5, 8. This also showed 1, 2, 3, 5, 8. Now that's enough talk. That's kind of useless, but it's not useless. You have to think of things like this. I'd actually discovered the Fibonacci sequence. Uh, yeah, I had actually rediscovered it, which was known from centuries, and the numbers were 1, 1, 2, 3, 5, 8. I'm just listing it. 13, 21, 4, 34, so on. The thing is, we take one number, we add it with the second number, and we form the third number. You see this? We have a number Fn, which is commonly used to denote a Fibonacci number. Fn, it is always formed by the sum of the numbers before it. 13 plus 21 is 34. Any number. You can check it out with any number. Fn is always equal to, for all Fn, equal to Fn minus 1 plus Fn minus 2. This is a great fact, and this is used in many fields, and the research is still ongoing. So that is enough talk of Fibonacci. Let's move on to the actual topic, which is recurrence relation. So this is a kind of a recurrence relation. It is a recurrence, and it is one kind of a recurrence relation. You know, you can define it for A n, B n, C n, D, T, D, S. You know, don't go after the variables. These are just variables, just like how x square plus y square equal to z square, where x, y, and z, just ignore that, that's my phone notification. X, y, and z are variables. These are just variables, and this term n minus 2 are just ignore it again, sorry, are just terms. Like it's the nth term, it's the n minus 1th term. Okay. The most common variables that we use are an and fn. Fn is used for the Fibonacci sequence, while an is used as a general term, like just like how x is. X is used just like that an. That was a brief introduction to the world of recurrences. Now, what is so a recurrence can be anything. An minus 1 is equal to 2 to the n. This is a great recurrence. 2 to the n plus an. This is also great recurrence. Just bring this to the other side. Anything can be a recurrence. An by 2 equal to a n log n to the power n integral of e to the n dn. This is of course e to the n. But this is also a recurrence. See? Anything can be a recurrence. Now the thing is, I'm not going to detail on how to solve recurrences. I guess Vedanta Olympiad School has a great video on that. Actual thing is, you have to actually uh, replace it by an element t or x, and you have to form a quadratic, and you get some complex number. I don't remember the exact value, and you have to solve it from there. But most of the questions that come in IOQM or any exam EMC are pattern recognition, recognition or combinatorial. So this is not for RMO as I have not qualified RMO. I have not even qualified IOQM. I'm not even sure. It's just a passion. So I'll probably not qualify IOQM, but I like this topic. I may or may not. I don't know actually. That's another topic to discuss on. But the results are not yet. Make sure to type in the results if the results have come. If you're watching this in the future. Okay, so enough talk. Now, an interesting thing is, you know, recurrences can be used for combinatorics. I've just told that, but it's very interesting. Let me give you a good question that is for a person who has never encountered a question like this. Before that, let me tell you that this is a very basic recurrence. Okay, like there can be combinatorial questions where you have to solve two to three variable recurrences and add them up. So it's just a basic recurrence. Okay, now you've given a string. You've given two numbers, one and zero. You've given one and zero, and you can form a number which does not exceed exceed 7 digits. Find the number. Find the number of numbers. Find the number of such numbers. Well, this is actually very easy because this is actually not even a recurrence problem. I'll show you two methods to solve this. Okay. But the thing is, this is not recurrence problem, but this becomes a recurrence problem with the exception that, not the exception, the restriction. No ones, no like, no one can stick to each other. Example, 0, 1, 1 is not allowed because these ones are with next to each other. No one's can stick to each other. Sorry about that. This is also not allowed. This is also not allowed. But this is allowed. This is allowed. This is perfectly fine. 0, 1. Why did I erase that? So we'll erase that example if you're sure about it. Now, just to give you a basic homework, without the restriction, this is very easy, and the answer is directly 2 to the 7. And that is very easy because just arrange this 1, 2, 3, 4, 5, 6, 7. This has two possibilities, this has two possibilities, this has two possibilities. 2, 2. Fundamental principle of counting. I hope you know this before learning recurrence because you'll not understand anything. So this is 2 to the 7. With the restriction, we'll play around with the question. Okay. We've got 7 digits. 6, 7. And you've got to find the number of numbers in which ones cannot stick. So Is 0 allowed? Absolutely. Yes, at the starting, because they did not ask 7-digit numbers. They asked the number of digits is either either 7 or lesser than that. Means you can have 6-digit or a 7-digit or a 2-digit. It does not matter. 0 comes. This is this is completely invalid. No, this part is considered as invalid, and this is choosing basic numbers. Like, so if 001 is coming, it's 1. So there. Now ones cannot stick to each other. Now let's consider two cases. This is not very intuitive. I don't think so. You can think of this on your own. It's not very intuitive. You cannot suddenly find a burst of energy and get the solution. You cannot find the reasoning behind the step unless you have known the step. The thing is, let's divide this into two cases. Case 1, when it you can either start it with starting 0, ending with 0, anything ends with 0. Case 2, when it starts with 0. Both the cases are good, and let's start with the first case, of course. When it ends with 0. When it starts with 0, that was starts and starts with 1. First case. So this is 0. Now, of course, the next number can be 1 or 2 or 0. And we let's define the number of ways of doing this as a n. This is just a variable, and n is the number of terms. Okay, e is a variable, and n is the number of terms. Suppose let's consider this to be not 7 n n. Why do you want it as 7? Okay, now what? Now I notice one thing. This can be filled as 1 or 0, and at the starting this could also be filled as 1 and 0. That's a that's a good observation. Both the things are the same. An is actually equal to an minus 1. The number of ways of filling. See, the number of ways of filling an is just like filling an is just like filling an minus 1. Does not make a huge difference because both of them are ideally free. One is the one which takes away the freedom. Just think of it like that. 0 does not cause any harm. 1 can appear in front of it and it does not cause any harm, and it just goes back to the old situation. It just brings it back to the old situation with just one term occupied with it. So this is just the old situation with one term less. So it's basically an minus 1. N minus 1 is the number of terms. I hope it's clear. N minus 1 is the number of terms. I repeated, n minus 1 is the number of terms because this is gone. And earlier it was n, now it has become n minus 1. Now this is en minus 1. And remember, we had divided this into two cases. We haven't missed any case. So basically, it's just the sum of both the cases. Now we've got the first case because it's the sum of both the cases because um, there are no other cases. What are the cases? What are the cases of a number? A number can be even or odd. Is there any other case? It does not make sense. It's like that. It can start with 0 or it can start with 1. And both the cases should be included and are the only cases. You can make sub cases like if it's 0, if it's 1. But it's not required here and I maybe teach it in another video. This is just for the basics. Second case. When it starts with this is a very crucial step. See, when it starts with 1, 1 essentially takes away the freedom. The number that appears in front of it cannot be 1. It can only be 0 because of the restriction. So this is automatically 0. You see, this is automatically 0 and there is no restriction on this. So this is just basically like the first case with with one more term less. In the first case, one term was less, and in the second case, one term is less of the already one term less. So basically, there are two terms here. You can see this one, two. These two terms have already occupied this, and we have taken two terms because one has essentially taken away the freedom. So we've got two terms less, and it's just basically add it here. This is the recurrence relation, and this is just basically the Fibonacci series. Now let me tell you one thing. This is the zeroth term. Okay. Actually, let's do one more thing. We'll do this here. In how many ways can you fill a single term? N equal to 1. You can fill it with 0 or 1. Makes no difference. So 2. Is it? 2. Yeah. It's 2. What about E2? In how many ways can you fill this? You can fill this as 1 1. No. You can fill this as 1 0 0 1 0 0. So this is 3. And how many ways can you fill a thing with 0 dashes? In 0 ways. Right? No, in one way, which is nothing. So A naught is 1, A1 is 2, A2 is 3. So do not solely rely on the thing that you've made, the bracket thing. You have to actually understand which is which and which is which. What is A1, what is A naught. So we have found this, and we have to basically find A7 because there are 7 terms. What is A7 now? We know this recurrence relation. So A7, I'll let you find that out. So A1 is 2. So now we've got this. So this is A1 is 2. So A1 is this is the first, this is the second, this is the second, this is the third, this is the fourth, this is the fifth, 23 is the sixth, 34 is the seventh, in fact 21, 34. So the answer should be 34. might be wrong, but the process is the same. So I'll let this as your homework. Let's solve this in the next video because I think that the idea of solving this in this video should be excluded because this is a bit more good as a warm up to an advanced video. So this should be a warm up for my next video. Post the solution down in the comment section. If you have any queries, you can just ask it there. I'll reply in every 1 week. So I'll reply to your comments tomorrow and after every week. So that's it. I'm your friend. I'm not a teacher. So I have no idea of advanced topics. So I'm just a stupid person, and I'm just trying to try to live out the passion of maths and share it with people more brilliant than me. Thanks for watching the video.